Today we're covering Zener diodes, including a number of applications, and one big don't. If you'd like to find out what that is, stick around. Welcome to the electronicsHobbyblog.com. I'm your host, Dominic Soldano, and today we're talking Zener diodes. So why Zener diodes? What's so special about a Zener diode? If you look at the characteristic curve for a Zener diode, it looks pretty much like the characteristic curve for any diode. There's some forward voltage leakage, and then a knee, and it goes into conduction at around 0.7 volts. Nothing special there. And when we look at the conduction curve for a reverse bias diode, it looks pretty much the same as well. We reach some reverse voltage, and it goes into reverse breakdown. What makes the Zener diode different is that it's actually meant to be used in the reversed biased condition. The first part of the curve is like any other diode. There's very little leakage current when it's first reverse biased. But at some point it reaches a knee, and then just past that knee it begins to conduct, and it enters the Zener region. That Zener region occurs at a very specific voltage that's set when the Zener diode is manufactured. That line runs pretty much straight up and down, so that it provides that exact same Zener voltage, V Zener, at a wide variety of currents. During design, we actually set the current to be at a specific point within the Zener region, IZT, and we set it far enough down the line that changes in current, either up or down, won't go outside of the Zener region. This way, the voltage stays constant as the current varies. Zener diodes come in a huge variety of values. I mean, I've got a surface mount component sample book here of Zener diodes, and you can see these start at 2 volts in this sample book, and they go all the way up, dozens and dozens of values, going all the way up to 68 volts. And I've seen through-hole Zener diodes that go much higher than that. I've got a 100-volt Zener diode in a through-hole component. Whatever value you're looking for, you're going to find it. Here are some typical specs and values for the 1N47 series of Zener diodes. You can see these start at 3.3 volts, and they actually go up to 100 volts. I'm just showing a part of the table here. But you can see some of those typical values, what the Zener voltage is. For example, the 1N4729 has a 3.6 volt Zener voltage, and IZT, so the point where you're supposed to set the current, is at 69 milliamps. And then the maximum that you want to set the current to in regulator mode is 252 milliamps, although it can handle a 1.26 amp surge. Let's take a look at how we would use one of these diodes in designing a regulator. You can see on the left is a representation of the curve, the reverse conduction curve. And on the right, we've got what a typical regulator circuit would look like. On the extreme right is the load, which we're representing as a resistor, but it doesn't necessarily have to be a resistor. It has some impedance that we have to take into account during the design. One thing that's critical when designing a Zener regulator is you need to understand the impedance or resistance of the load. So let's say we're designing a regulator, a 3.3 volt regulator for a 100 ohm load, 100 ohm nominal. And we need to figure out what that series resistor needs to be if we're starting with a 5 volt unregulated input supply. So we'll start by calculating the current through the load. If it's 100 ohms, and we're regulating it at 3.3 volts, we're going to get 33 milliamps through the load. Next, we'll set the Zener current equal to IZT, which in the case of this diode is 76 milliamps. So if the current through the diode is 76 milliamps and the current through the load is 33 milliamps, then the total current going through our series resistor is 109 milliamps. If the supply is nominally 5 volts and the other end of the resistor, where the Zener diode is at 3.3 volts, then we end up with a 1.7 volt drop across that resistor. Applying Ohm's law, 1.7 volts divided by 109 milliamps is 15.6 ohms. Series resistor needs to be 15.6 ohms. We probably won't find a 15.6 ohm resistor, but we could easily put a 15 ohm resistor in there and it'd be just fine. So let's look at how this works as a regulator. Let's say the voltage at the input dropped to 4.8 volts. That means that we now have a 1.5 volt drop across the resistor and that the current through the resistor would only be 96 milliamps. Since 33 milliamps goes to our load, 63 milliamps goes through the Zener diode. And you can see that we've moved up on the Zener curve, but not enough to take us outside of the Zener region. So the voltage should still hold at 3.3 volts. Now let's see what happens if the voltage at the input jumps to 5.2 volts. In this case, we now have 1.9 volts across the series resistor and 121 milliamps flowing through it. That means that 33 milliamps will still go through the load and 88 milliamps will go through the Zener diode. So now we've moved down on the Zener curve, but we're still within the Zener region. And so again, it regulates it to 3.3 volts. But here's where the big problem is with Zener regulators. What happens if we have a load whose resistance is changing or whose impedance is changing? For instance, in the case of a microcontroller, you're getting wide current swings in the load. Right? Microcontroller, at times it's only got a few transistors on, at times it's got thousands of transistors on, so the current changes wildly. So look at what happens if all of a sudden the load impedance goes to 10 ohms and the current goes to 330 milliamps through that load. The series resistor, well, the circuit just can't support it because it's going to try and draw 406 milliamps, 76 plus 330, through that 15.6 ohm series resistor. And there just isn't enough voltage in the circuit. You can see it would have to be 6.33 volts, and meaning the supply would have to be somewhere around 10.6 volts. So that's a problem. And this is actually a big problem in general with Zener voltage regulators. They just don't work when you have wild current swings in the load. They work just fine if you have a very stable load at a fixed resistance. But when you have a wildly varying load, a Zener regulator isn't going to work. Don't do it. Just don't. Don't. It's no good. Don't. Zener diodes make horrible voltage regulators. Don't do it. I want to show you how a Zener diode regulator performs. This is essentially the same circuit, but different values. The Zener diode that I have is 3.3 volts, and IZT is 20 milliamps. And I've set it up with a 1 kilo ohm load on a 5 volt input supply. So with 3.3 volts across the 1 k ohm resistor, that's going to be about 3 milliamps, 3.3 or so milliamps. And then I've got the Zener diode, which needs 20 milliamps for IZT. And so with 20 milliamps and 3, that's 23 milliamps. And a 5 volt supply, there's a 1.7 volt drop across that series resistor. And 68 ohms gives us about 23 milliamps. Actually, it was 72, but opted for the 68 ohm resistor since it was close enough. And you can see at 5 volts in, it's holding at about 3.26, 3.27 volts. And let's see what happens if we have a 0.1 volt dropout. You see it's gone to about 3.24, 3.25 volts. And if it drops out some more, down to 4.8 volts, it's at 3.22. So not too bad. I mean, what we're seeing is in the tens of millivolts in terms of change. Let's go the opposite way. So at 4.9 volts, back to 4.9, back to 5, back to 3.26, 3.27, and let's see what happens if it goes up by 0.1 volts. So 5.1 volts, 3.28, and then at 5.2 volts we get 3.30. So let's continue to raise that. 5.3, 5.4. So you can see these aren't as fantastic as, for example, a linear regulator, but they do have their place. However, Zener diodes make great voltage references. For example, if we had an Arduino and we wanted to provide a voltage reference of 3.3 volts at the AREF pin, which has very high impedance, so we can assume there's no current flowing into that pin, then we can take the Zener diode, in this case a 3.3 volt Zener diode, and set the current, the IZT, started out setting it at 76 milliamps and came up with a non-standard resistor value. So I picked the next standard resistor value, which was 22 ohms, recalculated the current. It comes out to 77 milliamps, and that's nominal difference. There's almost no difference to notice. So in this case, it'll make a great voltage reference. Here's another great application example for a Zener diode. You remember in our rectifier diode lesson, we talked about building in reverse voltage protection by putting a rectifier diode in series with our power input. Here, we can put a Zener diode in reverse in parallel with the power input, and we'll get over voltage protection. If the voltage at the input goes above 6.9 volts, remember there's going to be a 0.7 volt drop across the forward bias diode and then 6.2 across the Zener diode. If it goes above 6.7 volts, then that Zener diode will limit the voltage reaching the protected input to 6.2 volts. And here's an example where we're using a Zener diode to clip the top of a sine wave. When the voltage goes above 5.1 volts, the Zener diode shunts it, therefore limiting the output to 5.1 volts and chopping the peaks off of the sine wave. Here's another clipping example where we've put two Zener diodes back to back so that we can clip the top and bottom off of a sine wave. Notice that the output voltage reaches 5.8 peak and not 5.1 peak. You got to remember the 0.7 volt forward voltage drop on the second diode. Those two voltage drops will add up, and it'll clip it at 5.8 on both the positive and the negative peaks. And if for some reason you can't find a Zener diode in the value you need, remember Zener diodes in series add. By putting two 5.1 volt Zener diodes in series, you end up with a 10.2 volt Zener diode. You can do that with any combination of values. You just got to be careful to make sure that the IZT ratings for the Zener diodes are close enough to each other that you don't end up misbiasing one by too much. Well, I hope you enjoyed that and that you learned a little something. If you did, hit that like button and subscribe so you won't miss any future content. Till next time, cheers.